Taylor, don't ask me. All right, let's go ahead and get started. It is 7 o'clock.
Can I have my drive? Have my hard drive?
Yes, I have your hard drive. Yes. And no, I did not look at it.
Oh, it's okay.
They just gave me the hard drive and I brought it along with me. All right. So what we'll do today is I'll give you a new homework assignment. Okay? Yes, you guys like homework assignments. Yes, you do. So for the new homework assignment, if you know what you're doing, you know, it's actually like, oh really? That's a new homework assignment? Because it's a 4-bit subtractor instead of a 4-bit adder. In addition to the adder homework assignment, you now have a 4-bit subtractor homework assignment. I would suggest you not to get started with the subtractor until you're done with the adder. Okay? Because once you're done with the adder, you look at the equations for the adder, you look at the equations of the subtractor, and you go like, really? That's a new homework assignment? You know, 2 or 3 clicks away, save the file as a different file, turn it in, you're done. Yep.
Are you using the new submission box for the subtractor?
Sorry?
Are you using the new submission box?
Yeah, there's a new homework assignment for the subtractor, and it has a due date of next Thursday, so it's 2 days after the adder. Yep.
So I was looking at the half adder homework, but I think it has some of the half subtractor stuff on it because like it talks about.
Yeah, I fixed that. I fixed the last portion, right? You know, the equation stuff. Yeah. Yep.
I don't know. So maybe I was coming up with something wrong, but like a truth table for like how we did a truth table for addition, and how the carry bit is just the ending of the two.
Yeah.
Well, the truth table I came up for the borrow bit isn't one of the things.
Okay, let's take a look at the subtractor because you know, that. Well, let me point out where your homework assignment is. It's right next to the adder homework assignment, and then we'll take a quick look at the equations. So as usual, sorry.
Can you check to make sure the recorder actually on?
The recorder is on, and it is. Where is it? Right here. Yep, it is. It is recording. So far we don't have any technical difficulties. All right. So here's your 4-bit adder homework assignment, and I know what you're talking about. You know, at the bottom part, I only gave you the subtraction rules, and I fixed that to include the addition rules now.
See, for number 5, for like the requirements, it says A minus B.
Oh, for number 5?
Yeah, if you go scroll upward.
Oh, you mean here?
Yeah, see, A minus.
Yeah, that one has to be fixed. You know, it's for the sum, and this is A plus B.
And then the grading criteria has the subtraction thing.
Oh, I that part I can fix. You know,
Okay.
but I do want to fix the instruction just so that it's not confusing to you guys.
So no possible combinations.
Yeah.
Won't work.
True, but what I'm saying is, so then you can't use this because this doesn't imply.
So that's a sum, and this is a plus. There we go. Yep.
So for the subtractor, we'll have to use not the adders but subtractors, like half subtractor.
Yep. You'll make half subtractors, and then you make full subtractors, and then you stack up the full subtractors and end up with a 4-bit subtractor. Yep. All right. So what I'm going to do now is to show you the truth table of subtraction. Okay, and it is surprisingly similar to the adder. Okay. So instead of using the whiteboard, which is not easy to record, I actually brought along my webcam. You know, I think actually I can do that and record it by displaying the content of the webcam. But it's actually probably easier this way. So I'm going to show you the equations, and for that, I think a spreadsheet may work better. So I'm going to use a spreadsheet in this case. All right, so we'll just wait a little bit. There we go. Okay. So we want to do the, I want to show you both the adder and the subtractor so that you can compare and contrast the two. So we have x as one of the input bits, y as one of the input bits. Okay, so x and y are independent input bits into the system. So in other words, they're independent variables. But they're Boolean variables, okay? They can only be zeros and ones, okay? So I'll just kind of populate x and y here. X can be 0, and x can be 1. While x is 0, y can be 0 or 1. While x is 1, y can be 0 or 1. So this way we have exhausted all 4 possible cases for the independent variables. Okay, so we have seen this, again and again. As far as subtraction is concerned, okay, let's deal with addition first. So when we're dealing with addition, so I'll go ahead and insert a row here. Okay. So when we're dealing with addition, we have the R bit, the result, or the sum, if you will, and the carry, which is the carry to the next column. The result of 0 plus 0 is 0. The result of 0 plus 1 is 1. The result of 1 plus 0 is 1. The result of 1 plus 1 is a 0. And then for the carry bit, 0 plus 0 has a carry of 0. 0 plus 1 has a carry of 0. 1 plus 0 has a carry of 0. And 1 plus 1 has a carry of 1. That's the only one that has a 1. So what I will also do is to combine these two cells and say that and combine these things and say these are for addition. And there we go. And I'll just move these ones along here. Okay, so are there any questions about what you see in the spreadsheet up to this point? That should be a quick review of what we have been talking about already. So now we'll deal with subtraction. Okay. Now when we deal with subtraction, we also have a result, which in this case is the difference, and also a borrow. Now instead of saying it's a borrow, I'm still going to use C, because inside the processor, it really does not have an extra bit for borrow and one for carry. They are really the same bit as far as the processor is concerned. So instead of making this a different character like B, which kind of leads to confusion, I'm just going to use the C symbol, because inside the processor they use exactly the same bit to mean borrow. To mean borrow in a subtraction. All right, so let's focus on the R bit first, okay, which is the difference. What is 0 minus 0?
0.
Does it have a borrow of 1 or 0?
0.
Borrow of 0. Okay. 0 minus 1. Okay. So let me be clear here. Okay, this is still dealing with x minus y. With addition, it's not as much of a problem because it is commutative. But with subtraction, it is not commutative. So it's kind of important to know which one is being subtracted from whom, or from which other one. 0 minus 1 is what? 1 with a borrow of 1. Okay, very good. And 1 minus 0 is 1 with a borrow of 0. And then 1 minus 1 is 0 with a borrow of 0. Okay, wow. That didn't take too long. Okay, so when you look at column C and D, these two columns is reflecting the result of addition, which is your 4-bit adder homework assignment. When you look at column E and column F, that's for subtraction. And you can see that as far as the result R is concerned, it's exactly the same. So the only one that is different is carry. Okay, so in addition, carry is 1 if and only if both x and y are 1s. When you look at subtraction, the borrow or carry is 1 if and only if x is 0 and y is 1. Is that okay so far? So what kind of logical expression will give you a 1 if and only if x is 0 and y is 1?
Not x and y. Not x and y.
Not x and y. And then the other one is x and y, right? In logic sim, you can negate one of the inputs or both. Okay, when you look at the properties of an AND gate or OR gate, you can negate one or both, of the inputs. So I think I've just given you enough clues to get this assignment done. And let me just count the number of clicks that you need. 1, 2. So not including save as, and then turning the file and stuff like that. You just need 2 clicks to turn an adder into a subtractor. Because let's go ahead and go through one subtraction example. okay, because that will truly illustrate what I mean by that. So let's say we have 0, 1, 0, 1 minus 1, 1, 0, 0. Okay. That one may not give us all the combinations that I want. So let's put this stash of 1 here. Okay. So, and I'll do the same thing as last time. Okay. And we have one row explicitly just for indicating the borrow from the less significant digit. This is always a 0 because this column is representing the least significant bit. There can be no one contributing a borrow of 1 here, so this has to be a 0. 1 minus 0 is 1. 1 minus 0 is 1. And that's why a full subtractor is also made out of 2 half subtractors. Just like a full adder is made out of 2 half adders. And neither is contributing to this borrow. So this borrow becomes a 1, becomes a 0. And it's the same way as a carry. With a carry, both of the half adders of the same column can contribute to the carry of the next column. And in this case, both half subtractors can contribute to the borrow of the next column. Are we still doing okay so far? Okay. 0 minus 1 is 1 with a borrow. And since this will contribute to this borrow here, I can just stick a 1 here already because I don't have to wait to deal with the second subtraction of the same column.
Could you briefly explain?
Why is a 1?
Huh?
Could you briefly explain that carry of 1 with 0 minus 1?
It's a borrow of 1.
Well, borrow. Why is it?
0
0.
minus 1 has a borrow of 1.
So the borrow
And
is
a
go
result
here.
of 1.
But the borrow is go next one. Why is come to here?
Huh?
The borrow is go to the top of that next one. But
No, this
why?
is the way I write it. The bottom row is for the borrow bit.
So this row is the borrow, so
Yes.
which is like the result we come from the person.
This entire row is our borrows.
Okay.
And it makes sense to write it this way because, okay, let's finish this column first. 1 minus 0 is a 1. And then here we have 1 minus 1, which is a 0, right?
But
And then
we
we have this borrow. We subtract this borrow from this 0.
So which is
It's the same way you do base 10 subtraction.
you just need to convert it.
So 0 minus 1 is a 1 with a borrow. 0 minus 1 is 1 with one extra borrow all the way here. And then 1 minus 1 is a 0. So you can see that either one can contribute to the borrow here. The second last column has this 0 minus 1 contributing to this borrow of 1. And the second column from the right-hand side has this subtraction contributing to this borrow of 1 here, which is the same way as in addition. In other words, the way you combine the 2 borrows out of the 2 half subtractors to the overall borrow to the next digit is the same way that you structure a adder. Yep.
1 minus 0 is 1 and 0 minus 1 is. Oh, 1 minus 0 is 1 and 0.
Okay, which column are we talking about from the right? Sorry?
The borrow?
Which
You did 1
you mean
minus
this
0.
the row?
The first one? 1
Okay,
minus
which column?
First column.
Okay, least significant column.
You did 1 minus 0, that's 1. Borrow of 0, right?
Well, I didn't write this 0 until I performed this one. Because both can contribute, so I need to make sure that neither is contributing to that borrow.
Oh.
Yep.
What we're asking is why does 0 minus 1 create a borrow of 1?
Because
It's the same way as 0 minus 9 or 0 minus 1 in base 10 has a borrow, and then the difference is 9.
You can't get a value from 0, so you go to the next column to get it.
it's just a
if you
0.
have no money and I take $10 from you,
Yep.
you will have to go borrow something to pay that.
It's the same way as this in base 10. Exactly. Yep. Which happens a lot in Las Vegas.
Hopefully
Yeah,
that's
you
the time.
just showed it as 10 minus 9.
Right, it is the same thing as 10 minus 9 because you are borrowing a 10 from the next digit. Now, whether the next digit really has that for you, we don't care. We just say, hey, give me the 10. And then the next guy says, oh, I have no money now. Then they will borrow 100 from the next guy. And then the next guy says, I don't have money anymore. They'll borrow 1,000 from the next guy, right? It's the same way here, except this is a 1. This is the 1 can borrow a 2 from here. The 2 can borrow a 4 from here. The 4 can borrow an 8 from here, and so on. But it works out exactly the same way as base 10 subtraction. Sorry? Sorry? Huh?
Could I take a picture of that photo?
Can what?
Can she take a picture of that?
You can take a picture anytime you want to.
Have your permission?
When you guys take a picture, just let me know so I will hide.
Oh, there you go.
That's all. That's the only thing I have to do is when you take a picture, I'm gonna be here.
Like Vanna White. You should demonstrate.
Demonstrate.
Yeah.
Point. Yeah.
Like Vanna White.
I have a lightsaber at home. I can use that.
I don't know why it's not here right now.
Go ahead.
So like for the homework, the assignment says that we have to use 4 full adders in the end, but we're allowed to use 1 half adder and 3 full adders because technically you
Yeah, you can do it that way too.
You don't need to have.
Correct. Yeah, you can do that too if you want to.
Or the subtract.
Yeah, it doesn't really save you any work because you still have to have 4 things, connected together. Yeah. It does save you some time, execution time-wise. Yep. Any other questions? Is everybody kind of convinced that subtractors are pretty easy to implement? Yep.
Convert those to base 10, the result is, alright, so when you convert the first line to base 10, it's 5. You convert the second line into 14, and the result is 7.
Correct. Well, that's one way to look at it. The other way to look at it is this is actually -2. Now we haven't really talked about 2's complement just yet, okay? But one way to look at 1110 it is -2. It can represent -2 when we look at this bit pattern as a signed number. So in that case, it makes sense because we have 5 minus -2, which is +2, and we end up with a 7. Yep. But I'm not going to confuse you guys just yet, okay? But it still makes sense because there's one extra 1 here, which means I'm still borrowing from. This is 1, 2, 4, 8. I'm borrowing from a 16. So when you add 16 to, the end result, it still makes sense. Yep. So this is basically outstanding debt that is unresolved. All right. Any other questions? So base 2 it really is not that much different from base 10, except it is easier. It's just not easier because we are so used to base 10. When we look at 0 minus 1 is 1 with a borrowing, we're like, doesn't make sense because 0 minus 1 is clearly 9 with a borrow. But that's base 10 thinking. It's distracting.
I was about to say you would have known because everybody's eyes.
Yeah, everybody's looking that way. I should put my own picture as a screensaver, then you look back this way. It's like, oh no. All right, yep.
So unlike with addition, it's actually really important that you carry the operation all the way down for each column before you continue to the next.
Just like with addition, yes.
With addition, weren't we able to only go halfway? So we figured out what the carry was, but we didn't do the final step underneath the second line.
This is the same way too.
Bit, right? So you're saying the last carry, the very last one? No, so
if you just change that to plus sign.
So look at this. So if we would do 1 minus 0, and then we'd say that's 1 with a carry of 0, and then we would move on to the next bit before doing the last step with those two numbers that we just found.
You want to finish both subtraction before you move on to the next column.
With this one, yeah, but with addition, you
it's
don't
the same way.
You do?
With addition, it's the same way because either half adding can contribute to a carry of 1 to the next column.
Okay.
So it's the same way. You still have to finish one column before you move on.
Okay.
All right. Any other questions? Now there might be some questions about how to use logic sim, like how do you create your own component at several levels. So I have a demonstration scheduled in today's lab just to show you guys how to do that. So if you look down to the bottom part here, I have a lab demonstration today to talk about how to deal with hierarchical structures in logic sim. Okay, so for those of you who are kind of struggling and don't quite get how to create your own library part, so to speak, and instantiate it in a different design, and then use that one in return to main design, this will help out. Okay. Now, obviously, I'm not going to do the homework assignment. So what I'll do, let me just kind of click here to describe what it's going to do, is I'm going to assume there are only NAND 2 gates. So from the NAND 2 gates, I'm going to create a NOT gate, a AND 2, and an OR 2 gate from the NAND 2 gates. Just like what we talked about earlier in the semester sometime last week. And then from that, I'm going to create a exclusive OR 2 gate. So it will still be able to, I will still be able to show you how to create library parts at several levels, and all the commands that you need to use in LogicSim to do it. But apparently, it has nothing to do with the homework assignment.
For the homework assignment, we can use lang and X.
The homework
XOR.
assignment clearly states what you can use. Yeah, so you have to read the homework assignment.
Yeah, I saw there.
Yep. All right. Any other questions? No other questions? Okay. If there are no questions, we're pretty much done with this chapter or this particular topic. So let's go back here.
Well, okay.
Yep.
I don't know, say no, but is it possible, since we're talking about addition and subtraction, could you do one with a 16-bit number?
A 16-bit number?
Yeah.
We can do a 16-bit number. It just takes longer
Well,
compared to a 4-bit
small
number.
one but something where we have a carryover. I want to see something.
A carryover
To the next, to where, so say you're adding F and 3, something that's going to carry a value over into the next column.
Oh, okay, sure.
Yeah.
So you want to do it in base 16 or base 2?
Base 16.
Base 16?
Yeah.
Okay, sure. What do you want to do? I know what. This is something that I do every year.
Yeah.
It's F, E, E, D, D, A, D. Feed dad. Okay? And we can do this in this class because, this is a hexadecimal number. This is a hexadecimal number, right? Okay. So what is D plus D?
That is 13 plus 13.
It would be the same thing as 13 plus 13, okay? But that's in base 10, right? So in base 16, what is 26?
It is
16 plus 10, right?
16 plus 10.
And 10 is represented by A, and with a carry of 1. So now we have E plus A, which is 14 plus 10, which is 24, plus this one is 25. 25 in base 10 is, sorry?
16 plus 9.
16 plus 9, so this would be a 9 with a 1 here, because it's 1, 9 in base 16. So now we have ED and a 1. D plus 1 is E, so we have E plus E, which is 14 plus 14, which is 28. 28 minus 16 is 12. 12 is C with a carry of 1. So now we have F plus 1. F is 15 already.
Wait, you
15
said it
plus
was 12.
That's G.
Okay, well, yeah.
Because
we
12
subtracted
12
from
in
the
base 10 is C in hexadecimal.
No, because we subtracted from the 20.
Right, exactly. So now F plus 1 is, F is 15. 15 plus 1 is 16. 16 minus 16 is 0 with a carry. So we have 1 extra carry at the end. Yep.
What happens to that extra carry?
This extra carry bit?
Yeah.
That is a good question. Because in the notes here, you can see that in the syllabus, I'm supposed to talk about the carry flag and the 0 flag. This extra carry is not lost, but it is yet not stored as a part of the result. Because when you have 16-bit numbers, you have 16-bit numbers. You cannot store a 17-bit number because the sum requires 1 more bit. So this bit is just, kind of hanging around, but it is stored as a flag, what we call a flag. A flag is nothing more than just a binary number that is accessible to the processor, but it's not like you can use it for general purpose calculation. There are certain instructions that has specific access to the extra carry flag, but it's only from the previous add or the previous subtraction. It's not really the same thing as an overflow. I would not call this an overflow because overflow has a different meaning when we talk about sign numbers. So this simply means that there's an extra carry that we cannot store in the actual result. Yep. Okay. Any other questions about base 16, addition? Subtraction, same way. Okay. So.
Okay, then never mind.
Okay.
Same.
Okay, the class has spoken. All right, well, we are done with data and number representation. We are now moving on to von Neumann machines, which is the next slide. Now, von Neumann is an interesting guy. John von Neumann, or I think you told me that it's pronounced von Neumann.
Von Neumann, yeah.
Von Neumann.
Yes.
Okay. So this is a really short slide that talks about before and after von Neumann. Before von Neumann, computers are they have memory to store data. Okay, numbers to be crunched, numbers to be presented, and stuff like that. But the instructions were hardwired. In other words, you actually physically connect wires from one part to another part. Everything is hardwired as far as the behavior of a program is concerned. So there's no such thing as, I want to download a new app. No, cannot do that. If you want to reprogram a computer, you better be prepared to get your hands dirty, right? Because you have to open up the case, and then you look at all the wires, and then you have to figure out, okay, which wire has to go where. It's a mess, okay? So every time you want to change the program to do something else, it is a big mess, okay? It's physical activity. So this computer is a picture of the Colossus. I'm hoping some of you, I have not watched that movie yet, but I am going to. It's called The Imitation Game. It talks. Huh?
Turing called the Christopher in the movie.
The Christopher?
Yeah, it was his friend's name.
Oh, okay.
And he died at a young age.
Oh, okay.
Yeah.
Well, Turing pretty much died at a young age too.
Oh yeah.
Yep. Okay, but later on, ENIAC. This is a picture of the ENIAC computer, and the ENIAC did not have the ENIAC did not have von Neumann architecture either. So the ENIAC can be programmed, but if you just read the text here, it took weeks to reprogram. Okay. It's not just like, download a new app, install it, and you're all done. Okay, you actually have to have people to look at the schematic, go in, and basically do all the rewiring in order to change the behavior of a program. So that means programs were hardwired into a computer by electrical switches, wires, plugs, and so on and so forth. If you have taken a class in electronics technology, you probably know what a breadboard is, okay? So it's almost the same thing. You have like lots and lots of wires, and you have to figure out, which wire should go where when you're reprogramming a computer, those older computers. So it's until this guy came along, this is von Neumann, John von Neumann. When he came along, he figured out, amongst many other things, he figured out it's like, hey, if we can store data, numbers, and stuff like that in the memory of a computer, why can't we store instructions? Why can't we store bit patterns that can instruct the computer what to do? Why do we have to hardwire everything as far as the program is concerned? So he basically proposed and say, let's store instructions into memory as well, along with the data that it is supposed to process. Is that working out okay so far? Okay. So he is the guy who came up with this idea. And for those of you who are curious and have the time, you might want to look up his Wikipedia page, because this is only one of the many contributions that this guy has made in his relatively short life. He died in his, what, 50s, I think?
Mhm.
Yeah. And he is called a genius of geniuses. Okay, what is the plural of genius? Geniuses? Genii? That's the first one that came up with to my mind is genii. He worked alongside with a lot of bright people, physicists, statistician, mathematician, and so on and so forth. And they all look at him and go like, wow, he's in another league. So you might want to look up his Wikipedia page and just to understand how smart this guy really is. He died early because of radiation exposure, because he also helped build the hydrogen bomb. So, as a result, people suspect that he got a radiation poisoning, and that's why he died at a younger age as well, 50-something. He also shared the hallway with Einstein when he and Einstein both taught at Princeton University. And this guy likes to play loud polka music. And I think Einstein is not very fond of loud polka music, and he didn't care. He just played this music. So, kind of interesting guy.
He came up with game theory and all sorts of stuff.
Oh, he came up with all kinds of stuff. He came up with how to do computation in a noisy environment using statistics. Yeah.
Isn't Nash responsible for game theory?
What?
Is it Nash responsible? John Nash.
I cannot remember. Yeah, but he's an definitely interesting person. So his idea is really that. I mean, just the concept of, let's store instructions also into the memory of a computer. To us, it's like, that's nothing new. We do it all the time. But at the time that he came up with the idea, it was radical. Okay, nobody before him came up with that idea. If you just kind of think about it, if he did not come along, we wouldn't have computers the way we do now. Just think about it. Yep. And yet, when we think about computers, what pops up in my mind, in our minds, would be Bill Gates, Steve Jobs, and to some people, Steve Ballmer, in a slightly different way. But you know what? Along the way, we have Turing, we have von Neumann, and then we have all the other giants, that basically made computers the way they are now. So we kind of have to. Sometimes we have to remember all that stuff.
Hopper.
And also the inventor of C.
Oh, Ritchie
and
Thompson.
Yep. So there are many, many people who came along to make it possible.
Yeah. No, because she was like.
Okay.
Yeah.
So next, okay, Linux commands. Let's not worry too much about that. Bad return.c. We'll revisit this later. I have no idea.
That's a new scientist.
I think it's from next door, right?
Sure.
Or is it in my mind and you guys somehow hear the voices in my mind? Yeah, just try to tune out all the voices in my mind, because that may not be healthy. All right, so what we'll do now is to focus on one thing first, okay? So what we're going to do in this class is to focus on just memory, okay? Because the processor is kind of like a beast, it's complicated and stuff like that. Memory by itself is not quite as complicated. So what we'll do is we'll focus on memory. And I'm going to use LogicSim as a demonstration. And this slide here, this is something that I prepared last night to basically talk about what a RAM module looks like in LogicSim, and an explanation of all of these different ports. Now, don't worry, you have all this in writing already. What I'll do today in class is not to read my own notes, but to give you a live demonstration of LogicSim. So we're going to do a little demonstration of how to write some content into memory and how to read content from memory, and this way you will have an idea of how RAM works inside the computer. Yep.
I have a question. If this is all stored as just random, well, not random ones and zeros, but sequence, computers can be off for years, yet that information is still stored there. How does it stay in? How does it stay in if it's just electrical impulses?
It's not electrical impulses. In this class, we don't really talk about the actual gate level design of memory. There are basically two main types of memory. You have static RAM and then you have dynamic RAM. Static RAM, as the name implies, is static. In other words, the entire system can stop clocking. You can basically pause the clock of your entire system, and static RAM will still be able to maintain its content. As long as you have power supply, VCC, and ground, a static RAM chip will be able to maintain its content pretty much indefinitely. Okay. So if we have static RAM, what do you think is the other type of RAM? Dynamic RAM, DRAM. Okay. Now with DRAM, now most of you probably have not encountered the term DRAM, because you encounter the term SDRAM, which stands for synchronous dynamic RAM, random access memory. So with dynamic RAM, you do need to refresh. Okay. In other words, it's kind of like it has the ability to retain the content for a certain amount of time, but it will lose that content after a while. So you have to kind of refresh it, every so often. And the refresh mechanism is called cycle stealing, because it will basically pause your processor and say, "Hey, processor, don't talk to RAM. We need to refresh the content, of RAM," and that's dynamic RAM. So if dynamic RAM is so troublesome and you have to refresh it once in a while, and you cannot maintain the content when there's no clocking, why do we use dynamic RAM? For one reason. The density of dynamic RAM is much higher than the density of static RAM. In other words, you can fit more bits within the same area on a die when you use dynamic RAM as opposed to static RAM. So that's the one reason why we use dynamic RAM. But in Logic Sim, that part is completely hidden. Okay, the fact that we are using maybe static RAM or dynamic RAM is not represented by this interface. We're looking at RAM at at a higher level, at a more abstract level. So let's go ahead and do it, right? So let's go ahead and start up Logic Sim, and then we'll give it a try. So we have java-jar Logic Sim. Here we go. And this is actually surprisingly fast. When I do this in Windows on the same machines, it's never really quite as fast. This loads up just like that, and this is only a USB 2.0 hard drive connection. Okay, so when you want to access RAM, it is a part of memory. And when you go to memory, we have all these flip-flops, which we don't really care about, at least for now. And we'll just go ahead and grab one RAM module. And when you grab a RAM module, I will magnify this, so don't worry about that. So when you select the RAM, it will give you address bit, and let me just move it, width, data bit width, and data interface, and the default is one synchronous load, and I'll explain all of that later. Okay, so one synchronous load store port, and I'll explain that later. So for the time being, we'll go ahead and magnify this portion so I can explain it. So what I'll do is I'm going to go through a somewhat superficial explanation of the RAM module, and then I'll go ahead and attach pins to it so that we can actually do some read-write operation. So I can show you guys what you need to do, the steps that you need to go through to write some content to RAM and to read some content from RAM. So what we'll do right now is just to point to each thing, each port or each interface, and I'll just do a brief explanation. This is the address port. Okay, the address port, and by the way, hover over it will also give you an explanation of what it is. And for those of you who like to read online help, if you go to the online help of Logic Sim, it has a really, really good explanation of all the parts that are built into Logic Sim. Okay, so that's actually educational all by itself. It's just reading the online help of Logic Sim. Okay, so getting back to a memory module, the A port stands for address bus port. And what it does is it attaches to what we call the address bus of a computer. An address bus is nothing more than a collection of wires, of traces, electrical connections that is shared between almost all components on a computer. So if your computer has a processor and 4 memory chips, they all share the same wires as far as the address bus is concerned. Is that part okay? And in this case, because of the way I chose it, if you remember earlier, it showed that we have the width of the address bus is 8-bit wide. So that means we can address exactly 256 locations on this particular memory chip.
Can you say that again? Can you say that again?
Okay, let me click on the memory chip itself so I can show you. So when you click on the memory chip, it shows the address bit width is 8 bits. That means we have 8 wires going into the address port. Now with 8 bits, how many combinations do we get? How many combinations of zeros and ones do we get?
2 to the 8.
2 to the power of 8, which is 256. In other words, if you want to enumerate the locations or the addresses of the locations on this memory chip, it goes from 0, 0, 0, 0, 0, 0, 0, 0, all the way up to 1, 1, 1, 1, 1, 1, 1, 1. Is that okay so far? Okay. So that part that only controls the address. In other words, if you look at the RAM module as a notebook, this is how I tell you which page to turn to. It has nothing to do with the content. It's just the page number. I specify the page number so that you can turn to a particular page. The content is going in and out using this little pin here. Well, what looks like a single pin is actually, once again, an interface to the data bus in this case. The data bus, as the name implies, is for data purposes, but this one is a bi-directional port, which means if you're reading from memory, it is an output from the perspective of the RAM module. When you're writing, then the processor is writing the signal, and the RAM chip is just listening and say, okay, so what is the content that you want me to write to that location? Is that part okay? The address bus is input only as far as the RAM chip is concerned, because the RAM chip has no need to say, oh, processor, I want you to read this location. No, it doesn't work that way, right? It works the other way around. The processor tells the RAM chip which location it wants to read. Is that okay as far as the direction is concerned? Okay. Now in this case, it is just coincidental that the data bit width is also 8-bit wide. That has absolutely nothing to do with the address bit width being 8-bit wide. These two are completely independent. It is very common for the width of a data bus to be 4-bit, 8-bit, 16-bit, 32-bit, and so on. But it doesn't have to. Okay? So when you're designing your memory, you can choose like 14 bits wide as one location. In other words, when you look at the data bit width, it is simply saying how wide is one storage location in the memory, and how many bits can I access at a time. That's basically what it is. Are there any questions at this point? No questions? Okay, so just like the address bus, the data bus is also shared system-wide. All memory chips and the processor and a few other peripherals will share exactly the same electrical signals as on the D bus, on the data bus. Any questions about that part? No? Okay. Now we will talk about these 4 little interfaces here. There are 4. One is kind of like hidden. This is called the select pin or the select port. It is also known as the chip select port. It is a port where if it is a 0, you can do all the stuff that you want to do with all the other ports, but if the select pin is not active, the chip doesn't really pay attention. It doesn't do anything. Is that okay? In other words, if select is a 1, then this chip is actually paying attention to all of the other ports and is ready to do something. If this pin is a 0, then everything else can be going on. You can just kind of imagine the RAM chip has the headphone on, it's just ignoring everything. The LD pin is what we call the load pin, L-O-A-D, load. So this one controls whether you're reading from memory or you're writing from memory. Unfortunately, it doesn't use the regular term, okay? Most chip manufacturers use the terms read and write. And instead, it uses the term load and store, okay? Now this one single pin is going to determine the direction of memory access. If load is a 1, I have to remember, which. If load is 1, it is the processor reading from the memory chip. So when load is 1, the data pins will be doing the output because it will specify the content of the location that you're trying to access so that the processor can read that content. On the other hand, if the load pin is a 0, then implicitly it is a stored access. In a stored access, the data pins will be inputs so that the processor can specify the content to write to memory, and then the memory chip will sample that and store that at the location, or whatever location the address bus is specified. Are we doing okay so far with the load pin? Okay. Clear is easy. CLR is just clear, which is also known as a reset pin. And it's very rare, I would say, that people use CLR as the abbreviation of this port. Is usually known as a reset port. Okay, so when this is asserted, all the content of this particular memory chip will be reset to 0. That's all. That's all it's going to be. Are we okay with all of these pins? Any questions?
Is that clear? That whole, like, I don't know how to describe it. For example, we have, because that chip is a small, that there, each one is small. Is this one is just for one chip or a lot of?
This is one single chip right here.
Oh, one single chip.
Yeah, this is one single chip. So what is missing is this little pin here. This is actually a pin. This is called a clock pin. And it describes here, memory value is updated from a 0 to 1 transition. So all of the other pins are what we call level sensitive, okay? A 0 means something, 1 means something else, okay? Usually it is active when it is a 1, which is contrary to actual real chips out there, okay? Real chips out there typically has what we call active low signal, which means when the voltage of a pin is low, that pin is actually quote-unquote asserted. Okay, whatever the function of that pin is active when the voltage is low. But in this case, everything is active high, which means when a pin has a value of 1, it is active. When it has a value of 0, it is inactive. Okay, so when in this particular case, this is called a clock pin. Now, a clock pin is interesting because it doesn't do anything when it is a 0. It doesn't do anything when it's 1. It only does something useful when it goes from 0 to 1. The transition from 0 to 1 will have this RAM chip sample the 0s and 1s and the data pins and use the address pin to indicate which location it has to update. And when this pin goes from 0 to 1, then the update occurs. So it's called a clock pin. Are we doing okay so far as the meaning of each port is concerned? So now we're done testing. Okay, so we'll have some fun, with accessing memory. Now, when you're dealing with a memory chip, you can actually click on it, and you can say, I thought there's a way to access the content. Right click, edit content, that's it. So you can actually go ahead and use an editor to change the content of memory. And in this case, you can see this is the entire memory. The scroll bar does not scroll at all. And how many locations do you think we have?
0, 16 times 16, no, 15 times 16.
Well, F in hexadecimal is 15,
So 15
and
times
that's
16.
F0 refers to the location of this particular byte here. So the last byte is actually location FF. So you are dealing with 15 times 16 plus 15, which is 255. But 255 is the location, okay? We have 256 bytes because the first byte is at location 0, 0. Okay? So you can click on each a location and change it. So I'm going to click on a random location and do something about it. Okay, so I'm going to click on this one and say, let's change that to 7D. Okay. So I just changed the content of one single location in this RAM chip, and I want to access it. Okay, I want to access it using bus operation. Yep.
Why is this in hexadecimal versus binary?
Because it's easier to type. In binary, you would have typed 8 digits to specify the content of a byte, but in hexadecimal, you only need 2 digits to specify the content of a byte. So it's mostly for compactness that we use hexadecimal instead of binary. Okay, so this is, sorry?
But what, is it hexadecimal that gets stored there or binary that gets stored there?
Well,
I mean, or can you store
remember,
both?
binary and versus hexadecimal or even decimal, those are all representations.
Yeah, that's
But-
kind of what I'm getting at. Is this entire memory chip that's only can do 1s and 0s? Or?
Yep.
And then it would normally actually be just 1 0 or 0 1 or 1 1. in
Right.
transition.
Yeah, but it will take a lot more space on screen, and that's why it chooses to use hexadecimal to represent the bit pattern.
Okay.
So, if you like to type 70, so it save as binary somewhere else, or
It's not 70. If I type 70, it is
No,
actually 70 in hexadecimal, which is 0 1 1 1 0 0 0 0.
so what does binary digit save like when you write 70? It shows how it display here, but it's saved somewhere else in a binary.
Everything is internally stored in binary.
But now it shows like 70. So it take like several binary digits to save somewhere. So like if you write 70 on your display, it save as binary in your memory somewhere. So in your memory location, if you type 70, so it save as somewhere in a binary, or that's the last location of the digit.
Okay, the internal representation is always in binary. It's just that when it's displayed in an editor, it will use hexadecimal to save space.
But now we are saving in a RAM,
Uh-huh.
so that's the last location of saving data.
Yes.
So if we save in a hexadecimal there,
No,
It's
we are
a-
not saving in hexadecimal, it's just a representation. So hexadecimal is nothing more than a representation of the bit pattern that is being stored at that location. And that location is 7, okay, it starts with a 7, and it will be 7 9 actually. That would be location 7, sorry, I take it back. It's location 7 8, and the content is 7 0.
yeah, so that's the thing.
But you can also look at it as binary location 0 1 1 1 1 0 0 0, because that's the binary representation of 7 8 as a hexadecimal.
Yes.
All right, so let's go ahead and try to access that particular location. And at this point, I'm gonna put this one on the side, and we'll go ahead and see what we can do. Now, you always need pins in order to control what a wire is experiencing. So we need to use a pin to attach to the address bus. We need to use 1 or 2 more pins to attach to here, and also all of the other ports. So we'll now go to wiring, where the pins are, and we'll pick one up and put it here. Now remember, the address pin is an input pin as far as the memory chip is concerned. So it is an input pin, it's not an output pin. Huh? Yep, it will complain, because remember what I said, the address port, the address bus port consists of 8 individual bits. Even though logically it shows you as one single point of connection, it has 8 different things in it. Right. So now we have an option. We got an option here. One thing you can do is to change the pin itself and say this particular quote-unquote pin has 8 bits. Then you can specify each individual bit that is connected to the address port of the RAM chip.
And this is where we would put that 0 1 1 1.
Exactly. So you can click on the axis, so you can then control which one is a 0 and which one is a 1.
Maybe they're using the
You're not in simulation mode yet. Okay, so it's the same thing with the data pin. Okay, so I will have another pin attached to the data pin here. Now with the data pin, you have to be more careful because the data port can be input or output. So we'll go ahead and flip the facing first to west, and then we'll make a connection, and then we'll fix the width or number of bits so it's also consistent with the data port. And so far so good because we don't need to specify which way we are dealing with at this point. Okay. The select pin is just one single bit. Okay, so a normal pin would do. So we'll have one normal pin here, and we'll make it face north, and we'll make a little connection here to the select pin. And then I'll just be lazy and duplicate this 4 times. Oh, I think I did it one time too many. Or 2 times too many. There we go.
We only need 2, right?
Hmm?
We only need 2 other pins?
Well, we got 4 pins down here. There we go. All right. So we have all the pins connected. We just have to be sure, which way your things are. And right now, all of these pins are input pins because they are all squares. If they're output pins, then they would have been circles, right? The only pin, quote-unquote pin, which is an entire port, that can be input or output depending on what you're doing with it, is the data pin. So right now, it is considered an input pin. But if we are reading from a certain location, that means it has to be an output instead of input. So I'm going to change this one so that it is no longer an input pin, and instead it is an output pin. And when it's an output pin, you can see that instead of being a circle, it has rounded edges, and that's an indication that this is an output instead of input. All right, so let's go ahead and do something with this. Okay, so we'll go into simulation mode, and what was the location again? It was 78. 78 is the address, right?
Yeah.
So we'll go ahead and flip all of these bits so it specifies the location 78. Oops. Okay, and you can see that it is addressing that pin, that particular location already, and it's already outputting, and that's because with these ones, when I turn it into a 0, when this chip is not selected, the output goes back to quote-unquote sleep, which are all the X's. The clock pin is not useful because I'm specifying a load operation. And clear, I don't want to mess with that because if I mess with this, a 0 is okay, but if I turn this into a 1, I would have lost all the content on this memory chip. Okay. So once again, you specify the address, you specify which location on the chip you want to access, and then you turn on, and then you specify the load pin to specify whether you are reading or writing. And if you are reading, then you turn on the select pin. So you make the select pin a 1, and then the output will be available at the output port, just like that. Oops. Because I need that too. Otherwise, it would consider it to be a write operation. The process is writing to RAM, so that's why it's not showing at the output port.
Are they not supposed to be the same?
One is specifying the address, the other one specifies the content. In other words, if you want to have an analogy of things that you're familiar with, A is kind of like the index into an array, and D is kind of like the content or the value of a particular element of the array. Because you can always look at memory as one big huge array and say, okay, what is the index? Okay, the index in this case is 78 in hexadecimal, and what is the value stored at that location? It is 70. Are there any questions at this point? Let's see if we can store something into this memory chip. Okay? So if you want to store something into the memory chip, you can no longer just use an output port like this. You will need to specify an input port in order to specify content to write to memory. So what we'll do is we'll go ahead and look at this one, and we'll, oh, I'm in the wrong mode here. Do this one, do a duplicate, turn the second one into an input port, and have it connected in parallel with the other one. Okay, and you can do that. Okay, it's okay. So now we go back into simulation mode. Okay, and we'll turn off the chip select and turn off this load pin here, and we'll also turn off the clock pin. Okay, and it will be best if we specify what we want to write to that location. What do you guys want to write to location? Well, we don't have to overwrite location 7.8. We can overwrite location 7.9. Okay, so let's go ahead and overwrite location 7.9 with the content of what? What do you guys want? 1. 1? Okay, so we'll overwrite location 7.9 with a content of just 1. Okay, so let's see how we can do that. Before we mess around with the select pin or the clock pin and stuff like that, we have to specify the address first. Okay, so the address is 7.9, which means this 0 has to turn into a 1. And then before we do anything else, we better specify the content that we are writing to the memory chip. And we want 1, which means it will be all zeros, except for the least significant bit, which is a 1. So now that the address bus and the data bus are all set up, we can now specify the other pins. The first pin I'm going to mess around with is the load pin. Okay, so instead of, oops, I take it back, it should be a 0 because a 1 means we are reading from memory, a 0 means we are writing to memory. So 0 is correct. We can now turn on the select pin, because until we turn on the select pin, the RAM chip is not paying attention at all to the address bus or the data bus or the load pin. Okay, so now it is time, now that we have set up everything, it's time to turn on the select pin so that this particular memory chip of all the memory chip is the only one who's paying attention. So we turn on the select pin. This chip is now paying attention. Okay, but the content is not updated yet. That's because the clock has not made a transition. Remember, when you are storing into a memory chip, the storing only occurs when the clock pin has a transition from 0 to 1. In other words, we call that edge sensitive. In fact, in this case, we call it rising edge sensitive because the signal is going from low to high, and it's only the transition that is signaling the RAM chip to store the content. So let's go ahead and do it. Click on the clock pin, so it goes from 0 to 1, and you can see right when we click this pin here, when it transitions from 0 to 1, then the content is stored. Now, when we're done with this, the clock pin really should be reset back to 0, and then we turn on, and then we turn off the select pin, so that this memory chip is now quote unquote dormant, is not doing anything anymore. So that's a write cycle, and then before this we had a read cycle. Are there any questions about the memory cycles, how to read and how to write? Okay, so according to this scheme, okay, if your objective is to read 4 bytes out of this memory chip, how many times do we have to update the address bus? 4 times, right? If you're accessing 4 locations, you have to change the address bus exactly 4 times, because every time you access memory, you have to specify the address, and if the address is not the same, you have to re-specify it. Okay? And that takes up a lot of time, because every time you change the address bus, you need to wait for the RAM chip to come up with the actual data of that location. Because the memory chip is designed so that you can do random access. That's why RAM is RAM. That's why we have RA in the RAM, random access. Okay? In other words, the RAM chip is set up so that you can access whatever location you want. The next location you want to access has nothing to do with the previous location. But many times we want to access sequential locations, right? Is that making any sense? So how can we speed up this process? More chip. And what about this? What about we have an extra mode of operation where we can tell the RAM chip and say, hey, you know what? I'm going to access a block of memory. They're all sequential. And from here on, I will only specify the beginning address, but then every time I clock you, memory chip, needs to move on to the next location. So then I don't have to re-specify the address with every access. That's the S in SDRAM, synchronous DRAM. And that means, between the processor and the RAM chip, there's an agreement. If the processor specifies I want to do it in sequential mode, then the memory chip understands there's an extra pin to control that, but the memory chip understands and say, okay, now we are just accessing sequential bytes, and I don't need to have new addresses to specify the location of the next byte.
But so on that side, so you said it's the processor that's it's gonna like update, it's gonna add what it needs to be at that next memory address to
The processor is really just your clocking, the clock pin, because you still need a mechanism so that the processor can synchronize with the RAM chip and say it's time to move on to the next location. So there is a clock pin somewhere to tell the memory chip it's time to move on to the next one. But that clock pin is usually shared between the processor and the RAM chip.
well, no, I think I was trying to wonder what handles the mechanism of like basically increasing the address bus by that one.
It's a MMU inside the processor. It's called a memory management unit inside the processor. So as far as you're concerned as a programmer, you really don't need to specify anything. But the hardware, a part of the hardware of a processor, which we call the MMU, the memory management unit, which is actually very complex, can handle that part. And that's why we also have DDR memory, double data rate. Go ahead.
And yeah, I just wanted to ask what DDR means.
DDR is double data rate, which basically means, okay, before double data rate, it will only change to the next location on the rising edge of the clock. So let's take a look at the picture. Okay, so there's a clock signal, and the clock signal is usually a very uniform, completely predictable waveform. Okay, and this is system-wide kind of thing. And with just SDRAM, it will increment the address and get the next location ready on either on just the rising edge. Okay, it might be the falling edge, but it's only one of the two edges. So this is the time when it will increment to the next location. This is the time it will increment to the next location. This is the time it will increment to the next location. The processor is operating off the same clock, so it knows, oh, okay, it's ready. I can read the data bus again to get to the next location, or I can write the data bus to write to the next location in memory. But this is really kind of slow because we can only do one read operation per transition, per rising edge transition. And this is just SDRAM. DDR is paying attention to both the rising edge and the falling edge. So that makes it double.
Yeah, so you get
right, because now you have twice the amount of transitions. Okay, now we have DDR2, DDR3, so I think with the newer DDRs, we can even sample here and here. But that's a very kind of tricky thing to do because at this point, there's no signal between the processor and the RAM. They kind of have to keep track of time pretty accurately in order for the RAM chip to update the data bus and then the processor chip to sample it at the right time in order to catch the data of this.
It's almost no longer digital. Like when you're taking that many samples,
it's still digital. They just have what we call a frequency multiplier to deal with this internally. Yep. So it's not, this is, I'm not going to ask you guys questions about DDR or SDRAM or stuff like that, but for those of you who are interested, this is basically the technology that we are using. So this is really neat when you're accessing sequential memory. But accessing sequential memory is not something that your program or your code is going to do most of the time, okay? Because you're going to access like 32 bits, 64 bits at the most, which is not worth the time to set up the memory chip to do this. So this is done because we have cache, okay? Now cache memory interfaces with DDR memory in what we call burst mode. So the cache doesn't really want to just cache a location. It wants to cache like a block. So it has a basic unit of number of bytes. And when the cache wants to refresh, when it wants to write out the content or read the content, it's going to say, oh, give me the next 64 bytes. And that's when the burst mode operation comes in handy, because you spend the extra time to set it up once, and now you just go clock, 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 clock to read all the sequential locations. So that brings up one important point. What if you have a program where sequential reading is not going to be beneficial? In other words, you have quicksort. Okay, quicksort is not well known for doing things in a sequential manner. Okay, so they're all over the place. So in that case, this is not going to help. This is only going to help when you're going in a kind of more or less in a sequential fashion. Bubble sort will help, but bubble sort sucks, because of the time complexity. So, so the other algorithm, the other sorting algorithm that is really sequential in its very nature is merge sort. So merge sort can actually make use of this feature because it has the locality to deal with it, and it also has this sequential nature because it's always going forward. It's not going forward and backwards. So that's why when you look at the technologies like this, you can always tweak the benchmark program to favor one design and not the other. It's not always faster. It's just that in general it is a faster mechanism. Are there any other questions about memory chips? A single memory chip. Are there any questions about accessing memory, read or write, when there's only one single memory chip? So here comes the next question. Do you think one memory chip is going to be sufficient for an entire computer? In some cases, yes, but in general, probably no. Right, so in general, the answer is no, okay? So now the question is, what if I need multiple memory chips in order to implement the amount of memory that I actually need? So let's say that this is back in the, I don't know, maybe 60s, okay? So one memory chip can only have 256 bytes. And I want to have 1 kilobyte of RAM, okay? So what do I need? I need 4 of these things, right? Okay, so let's go ahead and stash 4 of these things together. I'm going to start a new design here, and we'll have 4 memory chips. So we'll go to memory, and we say, okay, let's have 4 of these guys. So duplicate, duplicate, and now we have 4. Okay, so we got 4 chips. And I already told you guys that the address bus and the data bus and also the load and clear and clock, they're all shared. In other words, they all hook up to the same wire. Well, each one has its own set of wires, but they are all shared between the chips. So I'm just trying to figure out what is the best way to arrange that. Maybe this will, okay, we'll go ahead and squeeze in, but not too much. Okay, this might give me enough space, I'm not sure. The trouble are these 2 pins. So this will barely give me just enough space to do it. Okay, so we got it. All right, so we'll go ahead and hook up the wires. So we'll have a wire coming from here, and it's going to be shared between all the chips. Okay, so the address bus is one single set of conductors that are shared between all the memory chips. Same thing with the data pins. Okay, so the data bus is just one single thing. There are 8 wires built into it, but the first wire of these 8 will hook up to the same bit of every single chip. Are we doing okay so far with that? Kind of? Okay. The clock pin is going to be shared. So I'm going to pull it over here, and we'll just hook up all of these together like that. And the load pin is the same way. Okay, so to control read or write, we have the same signal going to all 4 chips. And so we seem to have a problem here because, okay, if they're all sharing all of these ports, how can we access a particular location out of the 1024 locations that we have here? And the clear pin, I'm not going to connect, because, it's just for resetting the content back to 0, so I'm not going to hook it up. Well, I'm missing one particular chip or pin for one reason. That one is not shared. That one is on an individual basis.
Select.
Which one? The select pin.
Select.
Okay. All right. So if I have 1024 locations, which means I go from 0 to 1023 in decimal, how many bits do I need to specify one of those 1023 locations? Or 1024 locations?
10 bits.
We need 10 bits. And the address bus is how wide again? It's only 8. How do we use those 2 extra bits?
It's just which chip is on it.
Exactly. Exactly. With 2 bits, we can select one of 4 things. And how many chips do we have here? Exactly 4. So even though conceptually, logically speaking, we have 1024 locations and require a 10-bit wide address bus, 8 of the wires are shared amongst all the chips. 2 of those wires is used to say, oh, hold on a second here, which one are we using? That's what those 2 extra bits are for. So now we need to specify that logic. It's like, okay, but how do we specify that? Now, the interesting part is when you go to wiring, let's see here. There's such a concept called a splitter. Okay, now splitter is useful in this case. And I'll just grab a splitter here. So a splitter has a facing, which is not the interesting part. It has a fan out. So in this case, we have a fan out of 2, okay, by default. It has a bit width in, bit width in is also 2 bits.
2 in, 2 out.
Fan out, and then we have appearance, left-handed, bit 0, bit 1. Okay, so that allows us to basically break out a multi-pin wire into whatever configuration we want. So in this case, we have 10 wires altogether, but I want to break it out to 2 on one group and then 8 on the other group. Is that right? Because we wanted the last 2, the most significant 2, to control which chip I want to access, the least significant 8 to control which location on that chip I want to access. Okay? So the way to do that is to change the fan out. Okay, we want to change this one to 10, and then we want to split between the top and the bottom so that we have bit 8 and 9 at the bottom, and then all the other ones on the top. Okay, I'm not sure you can read this or not. So I'm just going to magnify a little bit here, just for this purpose. So if you just look at this particular part here, you can see that bit 0 to 7 is logically grouped together as one bundle, and then bit 8 to 9 is another bundle. The input is 10-bit wide. Okay? So the input address is still 10-bit wide. So we'll go ahead and attach a pin to the input. And it will complain because this pin is by default just 1, or has a width of 1. So we'll change it to have a width of 10, so that will get rid of that complaint, right? And now we have to figure out what to do with these 2 ends. This one goes to our address bus, like that. And then what about these 2? What about bit 8 and bit 9? We have to use bit 8 and bit 9 to specify which one of the 4 chips we want to access. And then as it turns out, there's one particular part that is just perfect for this job. It is called a demultiplexer. So when you go to, let's see, plexers, we have a demultiplexer. And the demultiplexer looks like this. And you can actually see this is the input, these are the outputs. So the input of the demultiplexer in this case will specify 2 input bits or 2 select bits, and that will make it to have 4 output bits. Okay? So we'll have these two to hook up to, this is one ugly diagram. There we go. And it complains because, oh, wait.
You're going from 1 to 2, I guess? Or from 2 to
No,
4?
data bits is only one.
Input is only one still.
Yeah.
So that's 2, and we have 2. Oh, wait.
Yeah, the multiplexer.
No, I need a decoder, not a demultiplexer. Sorry. Decoder, that's what we need. So decoder is kind of like a multiplexer. I'll explain the difference later. But in this case, it has 2 select bits, and the enable bit is important because that's kind of like an overall global chip select. And this one is the enable, and this one is select. I think this one, that's ugly. There we go. So now this chip can now select one of the 4 depending on the 2 bits of bit 8 and bit 9 of the address. So these 4 will go to the individual select bit. So this one is going to go here. This one is going to go here. Wow, that just barely works out. We barely have enough space to do it.
If we have more, what are we going to use?
I think we're running out of space here. Sorry?
Go to the bottom chip, then you can use the other one straight
6.
across.
You have
Yeah, but it's okay. It just looks really ugly. But it still works out. Didn't have to be that way, that's right. Okay, I'll just go through one more thing. Yeah. No, that's not what I want. Go back. Undo. Okay, I just want this one to be out here, okay? Because this becomes the overall chip select. Okay? So I'm just gonna go through this one today, and then we'll be done. So we go to wiring. We hook up one single pin to this wire here, okay? Because this becomes the overall chip select. And by the way, you can turn off the tri-state or 3-state.
What does that do then?
Yeah, that's what it said too.
Tri-state means it will give you the X state, which means it's not driving.
Oh, okay.
And it's not sensing, it's just doing
Oh, it's just
nothing.
okay, and then you turn it off means
What
it's
is that?
either one or the other.
Yep.
If you use the one from the toolbar, it only has 2 states.
Sorry?
Okay.
If you use the
Did you
one
do that
from
right?
the input pin from the toolbar, it only has 2 states
Oh.
to begin with, as well as the output.
That'd be like-
Okay. And the same thing with this one. We can turn this one to not to use tri-state because otherwise it just has one extra state that we don't need to use. Okay, so this is the last part. Okay, the last part, I'm going to zoom out a little bit because this is really kind of hard to read. Okay, so after we zoom out, this is the new diagram. And what we want to do is I just want to show you one thing, which is, to select a particular chip. Okay, that's all we will do today, and then we can continue next time. And we want to, let me see if I can make this one longer.
You have to move the entire thing over to the right.
Okay, we are running out of space.
Yeah, you're at the edge.
You zoom out. Yeah.
We'll just move everything here, and then we'll make this one bigger. Nope, doesn't like that. I think these 2 are the most significant bit, and this is a 0. So we'll go ahead and in simulation mode now. Okay, we're getting into simulation mode. If I turn this one to a 1, it should select this one. Oh wait, this is a 1 0, which is a 2, and that means this one should be a 1. And we also need that too. So that's a select one. That's a global select. Yep. If I turn it off now. If I turn off this one and turn on this one, then we'll have this chip selected. So if I turn on this one, you can see that the output. So basically, these 2 pins, bit 8 and bit 9 of the address bus, is used to select one of these 4 pins to have the same state as the enable. So if I do not enable the enable, then they're all off. And this is how you can basically use multiple chips to implement a memory space that is bigger than what the capacity of one single chip can afford. So are there any questions about this picture? No. Is it kind of fun? No, not really.
Okay, on the
so-
computer.
Hmm?
Find memory and practice there.
Well, it's once you watch the video, you can definitely replicate this whole thing. But the most important part is to understand that memory is not implemented by one single chip. It's implemented by multiple chips. And we have a decoder to help us take the most significant bits of the address and decode it so that we know which chip it is supposed to access. And this is also why we can share the memory bus, because we can just address one particular memory chip at a time, so there won't be any conflict.
Well, let's go ahead. Somebody else had a question.
Yeah.
To access the form memory chip, we use one.
Say again.
How do we access the form memory chip?
How do we access this one here? 1, 1. Yep. So we have 0, 0, 0, 1, 1, 0, and 1. Any other? Go ahead.
Yeah, it was about like, if you were implementing a system for this, what would be since they're not sequential, each one of those has its own, 0, 0. How then would you permit, a programmer to not have to worry about that?
A programmer never has to worry about this.
Yeah.
This is all implemented by the MMU of your processor chip.
So then would say if you were the person instructing that to make it easier for the user, are we gonna, whatever encoding coordinates with the second memory chip there, do we make that F0 or something? Cause I'm saying if I give a memory address of F0, I can get it for our example.
Okay,
There's three places that happen.
but our address bus, the overall address bus, as far as software is concerned, is now 10-bit wide.
Oh.
We consider
into
those two
the-
extra bits as a part of the address bits.
Okay.
Except they're not passed all the way through to the memory chips, because those two are used for the decoder so that it can select one of the 4 chips.
And then it's reading the low order 8.
Exactly. So that means, I just want to conclude this and then we're all done. Yep. So the first chip is really corresponding to logically location 0 to 255.
Yeah.
The next chip is going to correspond to location 256 to 511. 512 to 767 is the third chip. 768 to 1023 is the last chip. So as far as software is concerned, that's what you see. But in terms of hardware, the MMU is taking care of chopping up the memory space into multiple chips, and it knows which one to use when you access which address. This is really uniform, but when you look at the Intel processor and most of the modern processors, they're much more programmable than this. In other words, you don't have to break the memory chips down by uniform sizes.
Oh, so you could just have.
Yeah, you can basically say the first chip select is corresponding to a memory chip of this size. The second chip select corresponds to this size, and so on.
Other than the physical cost of the pieces, is there any reason to not use them?
Well, okay, there's one particular reason. It has to do with I/O space, input-output space. The Intel architecture doesn't deal with that because it has I/O instructions, but the Motorola architectures, they do not have a separate I/O space. So what happens is, with a total space of 1024 locations, one of these chips will be missing. There won't be a chip here. But those 256 locations will now be corresponding to I/O registers. So your UART, for serial communication, your USB controller, your IDE controller, or SATA controller. So you need to talk to those peripherals too. And with the Intel processor, it has specific instructions. So that's why there's a separate I/O space structured like this, but separate from the memory space. But the Motorola chips do not have an I/O space because it doesn't have I/O specific instructions. So you're going to leave some holes in the memory space for input, output, or I/O purposes.
where's Motorola chips at? In their devices? Motorola chips are, I'm assuming, only in Motorola devices? Or, like when you said Motorola's design?
They're in tablets and stuff, aren't they?
Motorola, unfortunately, really has not done much with processor chips anymore.
They used to be Apples, but not anymore.
Right.
Smaller things.
So
Yeah,
who
that's
makes
what I'm saying, like, they're like more embedded phones.
who makes the cell processor?
Snapdragon.
IBM uses the what is the name of that processor? I'm drawing a blank here. Huh?
There's AMD, Intel.
No. AMD and Intel are pretty much the same architecture.
There's a Snapdragon.
You're not talking about the Power PC? No, not
Power PC, that's it. The Power PC. Who makes the Power PC chips? It used to be Motorola. It used to be Motorola making that chip,
And that was going to
and then
IBM.
IBM and Apple, came to an agreement and say, okay, we'll both use, this chip here, and then Apple said, I want to have low power chips. IBM said, nah, we're not going to make it low power. And then Apple says, oh, really? If the Power PC does not have a low power mode, we're going to go the Intel route. And IBM says, okay, fine, go the Intel route. And as soon as Apple went the Intel route, IBM just decided to change the plan and go like, we're going to come up with some low power chips now. They really just wanted to get Apple out of the way.
Oh.
Yeah, because they don't want to support Apple with their. It's not a competitor thing. They're not really exactly competitors, but IBM had plans to use the Power PC in mainframe computers, and they don't want to customize to Apple's needs because they're mostly dealing with desktop and laptop applications. So that's why they said, nah, we're not going to make any low power chips, just to get Apple out of the.
Like, that's not our business.
Out of their hair.
Didn't IBM say that Apple stole their designs?
Well,
It's a lot of thievery.
A lot of people stole from IBM. Microsoft stole from IBM twice. The first one was DOS. The second was OS2. and they never really learned the lesson, but now they do, because now they are supporting Linux. It's like, well, why let people steal? We'll just contribute, right? So they got smarter.
But a lot more stuff from Xerox.
Apple and Microsoft both stole from Xerox. Now Xerox is interesting. This part I may not want to have it recorded.